All right, so now we're going to spend some time learning how we actually do MO theory for polyatomics. And this is connecting back to everything we've learned with symmetry and how we can now integrate that to better understand these things so that we can have our model that jives really well with quantum mechanics. So great stuff coming at you today. So just a quick reminder here, we had all the conditions that we had to satisfy. We're going to have symmetry of our orbitals that we have to care about. We're going to have to care about the orbital energies, and we're going to have to care that they're in close proximity. Admittedly, this one is not going to be something that we're going to care about at this level, but definitely know that that is part of it, okay? So let's get into it and let's see how we can start building our molecular orbitals for larger molecules. So let's think about the molecular orbitals for a linear system of with two hydrogens on it and something in the center. So this could be like a beryllium, for example, here. So that could be what we're dealing with. So for building our molecular orbitals, hydrogen is going to be the easiest way we can start. We just recognize it's a simple s orbital. That's all it has. It's a 1s. It's our wonderful sphere here. It's going to make our analysis pretty easy. Things get a little bit more complicated when we look at our central atom here, whatever it may be, because now we're going to recognize in its valence shell, yes, it's going to have an s, but we've also got these three p orbitals that we're also going to be able to invite into our bonding. So how do we fit all of these pieces together here? So let's get to it. We could just do some crude analogies here and some simple drawings here. So we could say, well, if we want to do these, well, let's start putting them together in formats that we understand. So for example, over here, I could say, well, I've got an s orbital from hydrogen, I've got an s orbital from my other hydrogen, and I've got a third s orbital from that central atom. All of them are going to have the same phase because the sphere has just positive, positive, positive. So we're going to see overlap of those orbitals. Our linear combination works, and that leads to having a bonding character. So hey, we formed some sort of bond between whatever that central atom is and the exterior hydrogens here. The other bonding interaction we could see is if we used the pz orbital from our central atom and then combined it with the negative and positive combination of the s orbitals for hydrogen. So we don't have to have just a positive orbital. We could say it's completely negative. That would now jive with the negative positive of the p orbital. So again, we've got overlapping symmetries here. So therefore, we would have another bonding interaction. Cool. So we can form some bonds. If we look at the rest of our orbitals, let's think about the px and the py now. Note our hydrogens are over here on this side and over here. Those do not show any overlap, so they can't be symmetrically combined with the px or the py. So here we just have these leftover p orbitals that are just sitting here centered on the central atom. They are non-bonding because they're not part of that picture here. And then we could look at our final set of combinations over with psi 1 over here. We said we'd do the 3 positive combination, but we could also do a positive negative negative combination. But now we see, excuse me, when we do that, we're building in nodes here. So that is anti-bonding character. Same thing could be said as if we did the reversed of the psi 2 over here. So now I have the negative s with a positive lobe on p, the negative lobe of p on the positive s. So again, that gives us the anti-bonding character here. This is now how we could put this together. So we could do this. But notice I'm not using any math. I'm just making some hand-waving arguments and just drawing lines, and that's all I'm doing here. So it's not perfectly satisfying. The other problem is this is going to start to get really complicated if we move to anything bigger or more complicated than just a linear triatomic here. So we're going to need something a little bit more quantitative, a little bit more structured for further analysis here. So let's see how we could do this. Now thinking about something very similar, still an AH2 system here, but now let's look for a bent type of molecule here. Notice we are using the same things. Our hydrogens still are just 1s orbitals that we have to deal with. And whatever our central atom is going to be, it's going to have its s and it's going to have its 3p orbitals that we're going to have to bring into this. So starting with the same types of logic, but now we're going to have the problem of, well, now I have s orbitals down here with this one. How does that work in terms of symmetry? How does that work in terms of geometry? That's what we need to understand. The way we're going to do this, though, is by introducing a term called ligand group orbitals, which is abbreviated as LGO, where we're going to say, hey, all of our external connected atoms, we're just going to call our ligands here. We'll see that term a little bit more in the future. And we're going to treat these all as one orbital group. Which will feel a little bit weird at first, but it's actually quite natural because it fits in with, the full linear combination of atomic orbitals. So if I'm thinking about a bent structure here of AH2, well, one combination is a ligand group orbital could be the positive 1s, or I could have positive negative. Those are the two possible combinations. You might ask, what about the negative negative? Well, negative negative is just the same as a positive positive. It's the same symmetries. We're just reversing the signs, so it's not going to be a new piece here. So there's only two combinations we can have here. That should also be something that we should remember, because if we start with two atomic orbitals, we need to generate two molecular orbitals, or if we start with two atomic orbitals, we are going to generate two ligand group orbitals. Nothing is created, nothing is destroyed. Don't forget that. But now we can look at these and say, what are these going to look like in terms of symmetry? So, for example here, the positive-positive combination of an AH2 molecule, which is C2V symmetry, let's look at its character table. If I do the E operation, well, nothing's going to change. So if I look at the symmetry, the phase of my functions, doing an E, I go from positive, positive to positive, positive. So nothing changes here. We get a 1. Let's do now a C2 rotation. So if I do my C2 rotation, here's my axis here. So I would have now a positive, positive goes to a positive, positive, right? Again, we have that. And we could do that again for the other two symmetry operations. And for this positive-positive combination, we'd see that we get 1s all across the board. So we'd be able to easily see here, if I erase some of the stuff here, that we're going to have an A1 symmetry orbital for this positive-positive combination. So let's just go ahead and highlight that we have A1 symmetry for that orbital. But let's now look at this other combination where I have the this plus-minus combination, and I've already said it's got B2 symmetry here. Well, how did I determine that? Well, let's look. With E, nothing ever changes. They're all 1, so that's not surprising. But let's look at C2 for a moment. I go around my axis here. I'm going to go from positive, negative with my C2 rotation. Now I'm going to go to negative, positive. So this would be a -1 character. So that has to be one of these two symmetry labels here. Which one is it going to be? It depends on what we look at with all of our other symmetry operations. So other symmetry operations that I can look at, let's do the mirror plane here, the XZ mirror plane here. And let's do that one. So we've got our sigma V here. We're going to go from positive, negative. That is going to reflect across, and we'll see that we get now negative, positive. So therefore, this is also a -1. So by looking at our symmetry elements, our ligand group orbital has B2 symmetry. Cool, right? So just like what we've done before here, just working out what the symmetry of these ligand group orbitals would transform as. So let's start putting it together. And I said, let's use the example of water here because that is our perfect example of a bent C2V molecule. We're going to have the 2s and the 2p from the oxygen. And I can tell you that the energy of that is similar to that of our hydrogen ligand group orbitals. So for oxygen, we're going to have to consider our 3p orbitals and its s orbital as shown over here. Now, the thing that we need to know is to form orbital interactions between the oxygen and the hydrogen, we need to know that they have the same symmetry. So we can't just willy-nilly select which orbital we're going to connect with the hydrogen. It has to have the right symmetry. So how do we determine right symmetry? Of course, we're going to be looking at a character table here. So we just saw what the symmetries of our ligand group orbitals are. So now we just need to find out what is the symmetry of the px, the pz, the py, and our s orbital here. And we can do that by looking at our character table. This should be pretty easy to see that the px transforms down here is b1, the pz, here it is a1, and the py is b2. So the only one that might be a little bit confusing at this point is what do we do with the s orbital? How did we find out that it's a1 symmetry? Well, this we'd have to do our analysis of each of the characters. What happens to the sign with E? It's a sphere, nothing changes. What happens to the sign when I do a C2 rotation? Well, it's a sphere with one sign, nothing changes. Basically, anytime you have an s orbital, it will be the totally symmetric representation. So that's why it's an A1 in this case. Cool beans? Nice. And now we can start putting together the diagram. So I'm just going to lay the diagram out here and I'm going to walk through what each piece looks like. So first thing we should recognize, the p orbitals on our oxygen are over here. They're essentially degenerate, meaning that they have roughly the same energy, but the one thing that we should notice over here is that they now have different symmetries. So we can't just combine them willy-nilly, we'll have to combine them thoughtfully. We're going to follow the rules for atomic orbitals that we've set. So we started with 6 total input orbitals. I've got 1, 2, 3, 4 from my oxygen, 5 and 6 from my hydrogen. So if I start with 6 orbitals, I've got to generate 6 orbitals. 1, 2, 3, 4, 5, and 6. So I have made an orbital diagram that is consistent with the orbitals that I put in. Now, only orbitals of the same symmetry can combine, so this is where things are going to get a little bit weird. Notice, over here in my hydrogen, I have an A1. Over here, I have an A1. And over here, I have an A1. So in other words, I start with 3 orbitals of A1 symmetry. I have to get out 3 molecular orbitals of A1 symmetry. This is where things will feel a little bit weird because what ends up happening is I have my PZ and A that combine with this same orbital, so I get a lot of orbitals forming. So I form this orbital, and I finally form this orbital. The B2 states, here we've got my B2 for the LGO. Here I've got a PY that has a B2 symmetry as well. I used 2 orbitals there, so I have to form 2 orbitals. So I form this one, and I form this one. Last piece that I've got here, I've got my 1 molecular orbital that came from 1 atomic orbital. I had this lone B1 orbital, the PX orbital. It has nothing of similar symmetry that it can combine with, so here it sits. It is a non-bonding orbital. Notice it's not bonding, it's not anti-bonding, it's not contributing to the overall bonding, it's just having 2 electrons hanging out, not doing anything with bonding. So I am leaving out the energetic piece, so we're not going to worry about how do we space these out and how what one would go above another. That's beyond the goal of this course. What I want you to see is that it's following the same rules that we started out with molecular orbital theory, and now we are using it to build our orbital diagram. The last bit of this would tell us, hey, how do we fill in our electrons? Well, our 6 electrons from oxygen's valence shell. We've got 2 electrons from the hydrogen valence shell, so we have a total of 8 electrons. 2, 4, 6, and 8 here. So we'd see that overall, we find that this is overall going to form a bonding interaction because we have bonding electrons here. We have none in the antibonding, so we're going to form some bonds here between the hydrogen and the oxygen. We're going to have some other things happening here. But that's where we're going to leave this analysis and say, hey, look, everything works in the same way. We're going to skip out on things that don't make a whole lot of sense at this point or where we need PChem to really analyze them. So at this level, it's just saying, hey, how do we actually form these molecular orbitals? That's what we're doing. Another perspective is, what do these orbitals look like? We could actually get that at this level. So over here, I've got my ligand group orbitals. So I've got the plus-minus combination and the plus-plus combination down here. And those are going to interact over here with, for example, this orbital over here. And so if we combine them, we get something that looks like this. We also get something that looks like this. And our final combination here looks like this. And you can kind of see how this works and how we're starting to see the geometric addition that we're doing here. That's all I wanted to kind of show here, to show that you can figure out what the orbitals look like by just adding up what you have. If you want to know what the orbitals really look like, we have to recognize they are not defined as a perfect sphere, and they're going to start overlapping. What does that look like? Well, it looks more like this. So my A1 orbital, my 3 spheres overlapping. Now it just kind of has this kind of like nondescript bean look that it goes over here. And we can work out all of our orbitals by doing a geometric analysis. We're not going to do that in this course. I'm not going to ask you to do it, but I want you to know that we can do it. The other thing that's important is notice, hey, these all have symmetries. And you should be able to go back into the C2V character table and actually demonstrate that, hey, this orbital here has B1 symmetry. So going through and looking at the E, the C2, the sigma V prime, and saying, hey, if I did those operations, I'd see this orbital transforms as a B1 representation. All right. So I know that's a lot here. Molecular orbital theory, we're just kind of rushing through here, but I want you to take the high points and say, how do we use symmetry to now inform how orbitals form in our molecular picture? This all now works consistently with quantum mechanics. This is what it looks like. To go a lot deeper here, we'd need a lot more time invested here and another course worth of information. So we're not going to spend a whole lot of more time on here, but we will do a few more examples in the next video. All right, so that'll do it for this one. As always, when you have questions, let me know. Let's figure this out together. And until next time, be excellent to each other.